So we have a problem where Bob sees a skateboard in front of him, accelerates to get to the skateboard, and then jumps on a skateboard in which the skateboard and Bob speed off into the sunset. So what we're going to do is I'll just look at all of the parameters here, write them down. Looks like he is 8 meters away from the skateboard. Bob's mass is 75 kilograms. Skateboard's mass, or I guess it's a cart. I keep saying skateboard. The cart's mass is 25 kilograms. And Bob's acceleration is 1.0 meters per second squared. Now, this all kind of doesn't mean anything. I'm just trying to label things just so I can get it all on paper. And what we want to know is the velocity of Bob and a skateboard after all is said and done. So the thought process here is that, okay, Bob is about to jump on a skateboard. We want to know Bob and his skateboard's velocity after he jumps on. So that's a mass and that's a velocity, right? That's the velocity of Bob and a skateboard. We have Bob and the skateboard's mass independently. Mass and velocity is kind of momentum like, isn't it? MV. And so maybe we can use a conservation of momentum for that part. The problem is we don't know what Bob's velocity is right before he jumps on the skateboard. So what I'm proposing is a two-part problem. Part two being the conservation of momentum. So I'll just say that COM, conservation of momentum. And then part one, we need to figure out what Bob's velocity is right before going on the skateboard. That looks like a kinematic problem since we know what Bob's acceleration is as he's speeding along. So what I'm going to first do is now see, okay, well, Bob is 8 meters away. He's accelerating. What's his final velocity? That's not this, but something else. What's his final velocity right when he jumps on the skateboard? Okay, acceleration, distance, velocities. Okay, I think I know which kinematic equation that would be. That would be V1 final squared equaling to V1 initial squared plus 2a delta x. Okay. And this is from just knowing the parameters that are given in the problem and then making up your own that you see fit. We know that Bob starts at rest. So we can say that in the very first part of the problem, his velocity is 0. This is what we're trying to find. We're trying to find this, which would then go to part 2. His acceleration is going to be 1.0 meters per second squared, and his distance of running is 8 meters. So solving this out, we get that velocity 1 final is the square root of this becomes 16, and therefore the square root of 16 is going to be 4.0 meters per second. So that's just going to be a partial solution. Now, for the second part, we're going to use the conservation of momentum. Mass of Bob, the velocity of part 2. So V part 2, initial of Bob, plus the mass of the cart times the velocity part 2, initial of the cart, is equal to the mass of Bob and the mass of the cart multiplied by the final velocity of the Bob and cart system. So now we're going to figure out, okay, well, what's this thing pertaining to? It pertains to the velocity of Bob before jumping on the cart. We know that the cart was at rest at the beginning of the problem, so we say this is 0. This becomes a lot easier now. So now we have the mass of Bob, velocity to the knot of Bob equals to the mass of the Bob cart system times the final velocity, which we want to find out. V then equals to mass of Bob, the velocity to knot Bob, divided by mass of Bob plus mass of cart. And let's see, we know this to be 75 kilograms. We know this is 4 meters per second. This is 75 kilograms again. And this is 25 kilograms. Doing all the calculation, this ends up to be 3.0 meters per second. And that's our final answer. That's the velocity of the Bob cart system once Bob makes an impact with it.